Um, in talking about that general electric field theory, I'll be sort of pointing out a bunch of everything. I'll give you some time at the end of the day as well, sort of do some tidying up or some planning for your taping project, videoing project. Tomorrow I'm going to do a little bit more sort of theory, slight little word problem in there, and then the rest is sort of word problems and that kind of stuff. There's a day of drawing fields as well. So now I handed out all the copies, so I need to get my own. Absolutely. I yelled at those grade 12s for you, but I don't know how successful I was. Okay, so you have the handout. You should have like a highlighter or a pencil or some other. I'm going to be making some observations as we go. I don't have this handout digitized, so if I make a diagram or whatever, you'll just have to sort of draw it on the side at the appropriate place. So please follow along, and we'll go from there. Okay, are we all ready? We got our phones away, we got our handout ready, we got our pencil sharp, we're ready to roll. The space around a strong magnet is different from how it would be if the magnet were not there. Put a paperclip in the space and you'll see the paperclip move. The space around the black hole is different from how it would be if the black hole were not there. Put yourself in that space and it'll be the last thing you do. Similarly, the space around a concentration of electric charge is different from how it would be if the charge were not there. If you walk by the charged dome of an electrostatic machine, a Van de Graaff generator, for example, and I have one, do I have it there or has someone stolen it? No, it's there. Right beside Alex. Someone has disappeared with my grounding thing. I think Mr. Love has it. I'm not sure. You can sense the charge. If you have hair, your hair will stand up. If you don't, well, you just sort of feel it sort of buzzing through you. It's kind of a weird feeling. Hair on your body stands out just a tiny bit if you're more than a meter away and more if you're closer. Why is that? Alex, why do you think? Why do you think your hair stands out more if you're closer to the Van de Graaff machine? As you get closer, exactly. So that electric field, the strength, is stronger as you get closer. That's very similar to what thing we've already learned about. Gravity. Exactly. As you get closer to the center of the Earth, gravity is stronger. So electric fields are very similar in that sense. The space that surrounds each of these, the magnet, the black hole, and the electric charge is altered. The space is said to contain a force field. Force field. So we talked about electric fields, we talked about gravitational fields, and we talked about magnetic fields. Okay? This idea of a field is an important concept in physics, and I'll explain right away. So, 33-1, electric fields. The force field that surrounds a mass is a gravitational field. If you throw a ball into the air, it follows a curved path. Earlier chapters showed that it occurs because there is an interaction between the ball and the Earth, between their centers of gravity, to be exact. Their centers of gravity are quite far apart, so this is action at a distance. Pausing for effect and to give you an opportunity to highlight. Teaching you that skill that you'll need to have in post-secondary when the professor won't say, this is important, highlight it. You'll just know. Action at a distance. And I talked about this a little bit with gravity, right? If I want to grab Dan's beverage this morning, I have to actually, if I want to move it, I have to actually touch it, right? I don't have Jedi powers, right? That would be action at a distance. Now, if I take Dan's drink, and I let it go, gravity doesn't need to be touching, it just acts on it, right? Action at a distance. Where you go. Okay? Electric field is the same. There does not have to be contact. So action at a distance refers to a force without contact. So how do we justify, how do we explain how gravity pulls drinks to the ground? How do we explain how these electric fields work when there is no contact? And that's the idea of the electric field. Okay? And that's the idea of that next paragraph that says, the idea that things not in contact could exert force on one another bothered Isaac Newton and many others. The concept of a force field eliminates the distance factor. So the idea of this field is a way of explaining, it's our model, it's our theory for this, this contact force, or lack of lack of contact force. The ball is in contact with the field all the time. This is important, you guys. I hear you guys talking out there. This is the important part. Stop talking and listen. This is why you don't get this stuff. You have to listen. It's a valuable skill. If you can't listen, I'm going to have to move you. Stop. The ball is in contact with the field all the time. We can say that the ball occurs because it interacts with the Earth's gravitational field. It's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the mass of the Earth and other astronomical bodies that are responsible for the fields. I talked about, a couple weeks ago, I talked about, what's the movie? The Martian, right? Where they slingshot back around Earth, right? So there's Earth, and here's the spaceship, and, oh, is it going to work? Yes, it is. And they slingshot around the Earth. How come? Because they are interacting, and we drew this on the test, they are interacting with the Earth's gravitational field. They are in contact with the field. Does the field exist in a physical sense? Like, can you see it with special field glasses? No, it's just a way of explaining how this works. It's our model. We talked about that way back in February. So while there is no contact between the spaceship and the Earth, there is a contact between the spaceship and the field. And we know that as you get closer, the field lines get closer, get stronger. Same idea with an electric field. Okay, last paragraph there on that first page. Just as the space around the Earth and every other mass is filled with the gravitational field, the space around every electric charge is filled with an electric field. Why did I speak like that? Exactly. The space around every electric charge is filled with an electric field, a kind of aura that extends through space. In figure 33-2, a gravitational force holds a satellite in orbit about a planet, and an electrical force holds an electron in orbit about a proton. It's right at the bottom of the page. And oddly enough, the satellite orbiting the planet and the electrons orbiting the proton are weirdly similar. In both cases, there is no contact between the object and the forces are, again, in quotations, acting at a distance. How much space do you think there is between the satellite and the planet? A lot. Think about the moon orbiting the Earth. There's a lot of space in between. How much space do you think there is, relatively speaking, between the electron and the proton? Exactly. It's surprising how much space there is. Most of us are made up of empty space. There's none of what I'm talking. Some more than that. I'll just leave it at that. Fine, sure. Putting this in terms of the field concept, we can say that the orbiting satellite and the electron interact with the force fields of the planet and the proton and are everywhere in contact with these fields. In other words, the force that one electric charge exerts on another can be described as the interaction between one charge and the electric field set up by that. That's an important sentence at the bottom of that page. In other words, the force that one electric charge exerts on another can be described as the interaction between one charge and the electric field set up by another. And what did Newton say about those action forces? Every action force there is a equal and opposite reaction. We talked about how the moon pulls on the Earth. How come the Earth doesn't orbit the moon then? The Earth is much more massive, extremely much more massive. Same thing with electrons and protons. Now, in your research the last couple of days, did you find out the mass of a proton or a mass of an electron? Did anyone run across that? That's not a number that I expect you to remember. In fact, I think it's times 10 to the minus 31. Can't even remember. I think maybe 10. When I talk chemistry, I used to know that. Yeah, it is. Times 10 to the minus 31? Josh confirms that for me. Thank you. Okay, flip the page. An electric field has both magnitude and direction. Uh-oh. Alarm bells. What does that mean? It's a vector. Its magnitude strength can be measured by its effect on charges located in the field. Actually, I'll take a moment there while you write down on the side, the electric field is a vector. At the very start of the year, I gave you four, the big four I call them. They are displacement, velocity, acceleration, and force. Those are your big four vectors. This is number 5. Kind of like the fifth beetle. No one knows about it. Okay, so its magnitude can be measured by its effect on charge located in the field. Imagine a small positive, air quotes, test charge that is placed in an electric field. Where the force is greatest on the test charge, the field is strongest. Where the force on the test charge is weak, the field is small. And then there's a little star there, it's called a footnote. It's at the bottom of the page that I copied this from. And it says, the strength of electric field is a measure of how great a force will be exerted on a small test charge placed in the field. The test charge must be small enough that it doesn't push the original charge around, and thus alter the field we're trying to measure. If a test charge Q experiences a force F at some point in space, the electric field E at that point is E equals F over Q, and you're going to get some notes on that tomorrow. Electric field strength can be measured in units of newtons per coulomb. Did you get that? Who was asking me? Someone, was it, no? Will. Was it you? Someone was asking me what and newtons / coulombs was. No? Someone was. Newtons per coulomb, that's what you measure electric field strength in. The next chapter will show that its equivalent units are volts per meter, something that I never get to in grade 12. Okay, back to the regular text, second paragraph on that page. The direction of the electric field at any point by convention is the direction of the electrical force on a small positive test charge placed at that point. The word positive is important. Physicists, for no reason, have elected the small positive charge to be the test charge. And so, if the big giant object that's creating this electric field is also positive, what's going to happen to the little guy? He's going to go away. So we would say that the electric field here is away. But if the big giant charge was negative, and I bring in my small positive test charge, which direction is the electric field? Positive. And that, my friends, is a key difference between gravitational fields and electric fields. Gravitational fields always pull, attract. Do they ever push gravitational fields? They do not, but these guys do. Okay? Which is why we have to use a small positive test charge. Now, if Dan's beverage happened to be made out of antimatter, perhaps gravity might be pushing it away. But we'll leave that for another day. Okay, so positive test charge. Now, I can't stress this enough. If you get the positive test charge wrong on the test, every single directional question will be wrong and backwards. So you must know that a positive test charge must be positive. It is like not knowing red means stop when you're doing your driver's test. If you don't know that, pretty much automatic failure. Pretty sure. Okay, so that's kind of, was there someone that happened to? Went through a red light? Hold on. Okay, so that's sort of the idea of, the basic idea of electric fields. Let's go to the next section where it says electric field lines. There's not a whole lot more here, you guys. You got to listen to me for about maybe 10 or 12 more minutes. Electric field lines. Now, since an electric field is both magnitude and direction, it is a vector quantity. If you haven't written that down already or highlighted it, do so now. It's a vector quantity and can be represented by vectors. The negatively charged particle in figure 33-3 top, the one on the right there, is surrounded by vectors that point towards the particle. The particle were positively charged, the vectors would point away from the particle. The vectors always point in the direction of the force that would act on a positive test charge. The magnitude of the field is indicated by the length of the vectors. The electric field is greater where the vectors are long than where the vectors are short. To represent a complete electric field by vectors, you would have to show a vector at every point in the space around the charge, and such a diagram would be totally unreadable. Let me explain this in real language. We've got, on the top there, you've got a negative charge, right? Why do the vector lines point towards it? Braden? How come they're pointing towards it? You been listening? Yeah? What do we use for our test charge? Positive or negative? Positive. So my little positive guy, is he attracted to this negative guy? He is, and so all of the vectors point towards. Now, way out here, the field is weak, so we just draw a little one. In here, the field is stronger, so we draw a longer one. And what about over here? Well, even smaller. And what about like over here? You know, whatever. I could spend literally all day moving this guy around and drawing vectors. And what would I have when I was done? I'd have an entire page of black that you couldn't read anything. How come? Because there'd be a vector for every point. They'd be overlapping, it'd be a big mess. Completely useless. Okay? So the one on the top, just right on the side there, right on the top there, write vectors here. Those arrows in that top diagram are vectors. Do they show every point in space? No, they only show the start of every vector, what the strength is there. Okay, so now I'm going to go down to the next paragraph. A more useful way to describe an electric field is with electric field lines, also called lines of force. Where the lines are farther apart, the field is weaker. This is similar to the gravitational field strength we talked about. Where the lines are farther apart, the field is weaker. For an isolated charge, the lines extend to infinity, while for two or more opposite charges, the lines emanate or start from a positive charge, terminate or end on a negative charge. Some electric field configurations are shown below in figure 33.4. So what I'm saying is now, you got that picture on top that is now a big mess, but on the bottom, you got this, right? And now, these lines, are they vectors? They are not. They look like vectors, they're arrows. I wish they could, come up with a better way to show them, but they can't. So I emphasize the difference. These are not vectors. The top one are vectors, and these are electric field lines. And the difference is up here, it's the length of them that is the strength or the magnitude. And down here, the electric field lines, it is not the length of them, it is the how close they are, which is called the density. Okay? This type of diagram, much more useful, much more readable. If I had a bigger charge on it, if I were to put a bigger charge here, I'm going to put a double negative, triple negative, why not? What would I have to do to that diagram to indicate that? If I've got a bigger charge here, what would I do, Josh? How would I change the diagram, or would I change it at all? How would I change it, Clark? What would I do? Triple the line? Triple, like if I had triple charge, triple the lines? That's probably fair. I can't, you know what, I actually honestly don't know if it's triple or not. But certainly there would be more of them. And once again, the closer they are, the stronger they are, and the farther away they are, the weaker, because they are farther apart. Does that make sense? Do you guys understand the difference between this top messy diagram, which is a bunch of vectors and just all over top of one another, and down here? These are not vectors. These are electric field lines. Exciting stuff, right? No, not at all. At the bottom there are some electric field configurations. So on the left, we have a positive charge. How come those arrows point away? Austin, how come those arrows point away in that bottom left-hand one? Because it's a positive charge, right? It's a positive charge. The next one in the middle, you'll notice that the lines start at the which one? They start at the positive and they end up at the negative, because that's the direction that a positive charge would go. Once again, those are electric field lines. Well, the one on the right is called charge plates. So we have a positive plate on the left, we have a negative plate on the right. Again, the field lines go from positive to negative. Flip the page over, you're almost done. Photographs of field patterns are shown in figure 33-5. Now I apologize for the quality of your pictures because it's a copy of a copy. The photographs show bits of thread that are suspended on a vast surrounding charged conductors. The ends of the bits of thread are charged by induction and tend to line up end to end with the field lines, like iron filings in the magnetic field. Have you ever seen like those iron filings on a magnet? Ever seen that? Maybe as a kid. I have some here I can show you. Notice that between the plates, the threads are aligned parallel to each other. The field is a constant strength between the plates. This one here on the bottom left-hand corner is similar to that last one on the previous page. Those are two charged plates. And the field lines, what would you say about the lines between them? What would you say about them? I'm just going to quickly draw it here. Would you say that they are parallel? Or parallel-ish? What does that indicate? Equal, you know what, I'm not going to say equal. I'm going to say uniform strength. The field is the same everywhere here. What happens sort of at the edges? Kind of bends, right? And I'll explain why in a few days. It's not uniform then. Okay? What could you say about those top two pictures? The first one kind of looks like this. Oh, and I'm drawing arrows and I shouldn't be. And the other one looks like this. Don't draw arrows. This is really rough. There's a reason I don't teach art. What can you say about those two? We're almost done.
First one is a negative but a positive charge. Second one is both positive charge.
Does it have to be both positive?
Or both negative.
So she's saying that these are the same charges. And these are, could we say, opposite? Does that make sense? Would you agree? Andrew, do you agree? Yeah? How could we tell which one of these is positive and which one is negative? Or can we? We can't tell from the picture, right? We can't tell from the picture. The only way, you'll notice that I accidentally drew an arrow in there. I just drew it because I started here, that's all, right? I always start from the positive and go to the negative. But that's not true. You can't tell from the picture. The only way you could tell would be to bring in an actual positive charge and see which one is held. That's the only way you can tell. What do you say about the bottom one there? You've got the bottom right-hand corner. You got this, and then you got a circular thing, and then they're kind of going like this. Same charges or opposite charges? Opposite? How can you tell? Because they're going, one is going towards the other. We don't know which one. Last question for you. What does it look like inside that circle thing? It's just a big mess, right? What do you think? What kind of electric field exists inside that circle thing, Renee? What do you think? When it's just a big mess like that. No? You can tell me. I won't. No. Anyone? It's a tough question. In a sense, yeah. There is no field at all, exactly. Way to go, Josh. There is no field at all. Now, why would that happen? Why would there be no field there? If you imagine the whole thing to be positive, if you imagine, no, I mean the charge on the plate, right? Every positive charge in here is what? It's like a kid in the bear pit at lunchtime. Well, maybe that's a bad example, right? It's like being at country fest kind of. You're being pulled and pushed in all different directions. Right? You're in a big crowd. This poor little blue guy right here doesn't know which way to go, and every other one of them is the same. There is no uniformity. There's no direction to go. They are lost in the wilderness, metaphorically. Right? There is no field. Well done. Okay, last page, then I'm done. Promise. It's been a rough go here, I know. 25 minutes to listen to that. Whew. Then I'm done. I don't even like listening to myself for this long. Last one bit. If our only concern for electrical forces were limited to isolated point charges, the electric field concept would be of limited use. The force between point charges is adequately described by Coulomb's law, which is F equals some constant Q1, Q2 all over R squared. Blah, blah, blah. But charges most often are spread out over a wide variety of surfaces. Charges also move. We call that, when charges move, electricity, isn't it? This motion is communicated to neighboring charges by changing the electric field that emanates at the speed of light. As later chapters will show, the electric field is a storehouse of energy. The energy can be transported over long distances by an electric field, which may be directed through and guided by metal wires or directed through empty space. Okay, last little bit. Question there in the top right-hand corner. The nerd question. Suppose that a beam of electrons produced at one end of a glass tube and lights up a phosphorus screen on the inner surface at the other end. When the beam is straight, it produces a spot of light on the middle of the screen. If the beam passes through the electric field of a pair of oppositely charged plates, it is deflected, say to the left. If the charge on the plates were reversed, in which direction would the deflection occur? Hold that's a lot of reading. The opposite way. Okay, Josh, let's go 3 for $1. Who cares about stuff like this? Does anyone even have these, like, anyone but nerds have these kind of objects? These glass tubes and these phosphorus streams. Now, in the old days, when I first started, I could say, yes, each and every single one of you had one in your house. It was a TV. Who's got a big tube TV at home? Anyone? I finally got rid of mine a couple of years ago. Some of you might still have the big tube TV. I used to be able to go and point to it in the room. Okay? When you turn it off, Hannah, that big tube TV, what happens? Down to a single point. Here's how a TV works in 20 seconds. You got an electron gun, and it shoots out electrons at a glass screen that is coated in phosphorus. Phosphorus glows when it's attacked by an electron beam, right? And up here, and front and center, sort of in 3 dimensions, are plates that charge an electric field. And so your little beam of electrons is deflected, and it goes on the screen back and forth like this, then it starts over again, and then it starts over again, and then it starts over again, and it does that really, 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 really fast, and that's what creates the picture on those old tube TVs. And when you turn the power off, you cut the power to these electric plates, and that beam of electrons is shot right towards the center, and it doesn't deflect, and that's what that is. It just, right? There you go. There's your nerd talk for the day. Okay, I'm done. You got almost 30 minutes left. Okay, thank you. You have 2 possibilities. There are some think and explain, some review questions there. These questions here, you are responsible for. You need to know, be able to answer these questions. Okay, I can go through them at some point in the future if you want. These questions are based on what I just read and what I just talked about. Okay, some of them are easy, some of them are a little bit hard. Okay, if you feel that your next 30 minutes is best used by spending time with your group, getting some milk and stuff done, you do that as well. Unfortunately, most of the laptops have disappeared. There are some in the back. Okay? Bathrooms, go. If you need something else, go. Use your time wisely.
That's what I was going to ask you.